On behalf of Fred Kavli and the Kavli Foundation, I would like to first thank the Royal Society for hosting this event. It's my great pleasure to have the honor and opportunity to hear our speaker, Dr. Jane Luu, 2012 Kavli Prize Laureate in Astrophysics. The Kavli Prize is a partnership between the Norwegian Academy of Science and Letters, the Kavli Foundation, and the Norwegian Ministry of Education and Research. The Kavli Prizes are intended to do many important things. One is to reward the scientists who make significant contributions to society, yet all too often remain our unsung heroes. It is also our hope the prizes will provide an opportunity for a richer appreciation of the benefit of science. But most of all, and this is what Fred Kavli always emphasizes, that we hope the prizes, by honoring the important achievements of today's scientists, we stimulate the curiosity of our youth to themselves become the future pioneers of science. Practically everything we touch in our daily lives has been improved or developed through basic sciences. This includes our understanding of our world, ourselves, and our universe. For this reason, the Kavli Prizes recognize scientists for their seminal advances in nanoscience, neuroscience, and astrophysics. Fred Kavli, who is a wonderful man, many of you have met him in the past, who is the founder of the Kavli Foundation and the prizes, is frequently asked why he chose to focus on 3 particular scientific fields. He selected these areas because he believes they are of great benefit to humanity. These areas are also at the brink of great discoveries, and yet it's unlikely we will ever know all about these subjects, and we will run out of questions. Astrophysics, for example, is about answering some of mankind's greatest questions. How did the universe come into existence? Why does it continue to expand at an accelerating rate? And perhaps most fascinating of all, is life on our planet unique? Or in fact, quite commonplace? Today, science is taking us to the brink of amazing discoveries about the universe and making us aware of possible phenomena that seem incredible to imagine. The immense mass of stars and galaxies throughout the universe is only 4% of what is out there. The rest is what we call dark energy and dark matter, and we have very little idea about what they are. Indeed, this is the field of interest for today's speaker. She is recognized for discovering and characterizing the Kuiper Belt, work that led to a major advance in the understanding of the history of our planetary system. And so I thank you for this opportunity to hear from one of the great pioneers in astrophysics and astronomy, and to welcome Dr. Liu at the Royal Society, and again, congratulate her for receiving the Kavli Prize. Thank you.
Ladies and gentlemen, the Kavli Prize was established in order to honor scientists having done outstanding work within these 3 fields: astrophysics, nanoscience, neuroscience. The Kavli Prize in each of these categories consists of a gold medal, $1 million and a scroll. It is a partnership, as you heard, between the Norwegian government, the Kavli Foundation, and the Norwegian Academy of Science and Letters. The Norwegian government provides funding for running the operation. It's a celebration of science. The Kavli Foundation provides the funds for the prize, plus. And the Norwegian Academy of Science and Letters, we are responsible for selecting the prize winners within these three categories. And we do this by establishing a committee for each of the prizes. There is one Norwegian member from the Norwegian Academy in each of them, only one. The others are nominated by learned societies around the world. They are nominated by this society, Royal Society, by National Academy of Science, by Max Planck Association, the French Academy, and the Chinese Academy of Science. That gives an international ownership to the prize. I'm Nils Christian Stenseth, the Vice President of Norwegian Academy of Science and Letters. Science has always been important. And you just heard this quote by Fred. I stated it earlier today in the opening, and everything we have said 3 times must be true, and it is true. Fred Kavli has also said that science has an enormous impact on our health, economic standards, and overall quality of life, and continues to be of increasing importance. Science is becoming more and more important today. There is a lot of relativism, there is a lot of alternatives, but it is only solid science that beats it all. That's why it's important to honor people having done and exercised excellence in science. And the Kavli Prize and similar prizes are important in order to promote awareness for excellence in science. The Kavli Prize was awarded the first time in 2008 by His Highness the Crown Prince of Norway, who was here earlier today. And it is visibility of excellence in science is important. And we have banners with Kavli Prize on the main street of Oslo. People see this, become aware of it. The second time it was awarded was in 2010. Then our king was part of the ceremony. The third time was in 2012, in all 3 categories. And that year, Jane Luu was one of the prize winners. She's here today, as you know. But she got the prize together with Brown from Caltech and Hewitt from California, Los Angeles. And you have heard why she got, and they got the prize, it says here, for the discovery and characterization of the Kuiper Belt and its largest members, work that led to a major advance in the understanding of the history of our planetary system. It's a great pleasure to welcome you to the podium. You need no more introduction. We look forward to it. Please.
As recent as the late 1990s, astronomers thought that they knew everything in the solar system. They knew the contents. They knew about the planets, the satellites, asteroids, comets, and so on. The inventory of the solar system was thought to be complete. In fact, if you talk to the typical astronomer or anybody in the audience this morning, he or she would have questioned you why bother to study the solar system at all, since everything was known already. But I hope that this talk will show you that this is far from the truth, and there was a discovery of a new population of object beyond Neptune called the Kuiper Belt that turned this view upside down. So my talk today is about the discovery of the Kuiper Belt and its implication for our solar system and other solar systems. Along with the notion that the inventory of the solar system was completely known, astronomers also thought that they had a good handle on how the solar system formed. We know that everything in the solar system formed from the solar nebula, which is a disk of gas and dust swirling around the sun. And from there, the planets formed by binary accretion, which is a process, a growth process that occurred when two bodies stick together and they merge to form larger bodies. And this process was believed to occur at every stage, starting from tiny dust particles reaching large sizes on the order of 1,000 kilometers or so. It was never very clear how microscopic dust particles could grow into macroscopic sizes. So most theories tend to gloss over this point, and they tend to start at the stage where the 1 kilometer sized bodies called planetesimals already exist. The 1 kilometer size is an important milestone in the formation process. That's because at 1 kilometer, these bodies are now large enough to attract each other by mutual gravity. So as these small bodies start to accrete each other, large bodies begin to form because they collide, they stick, and they grow bigger. So during this phase of accretion, thanks to the larger gravitational pull, a few large bodies manage to grow much faster than the rest, rapidly increasing the mass inequality between them and the smaller bodies. It's kind of like capitalism, but in terms of mass. So this stage is called the runaway growth stage. The outcome of this stage is that you have a few very large bodies existing among smaller ones. What's there's left? So you have a few big bodies on the order of, say, a few thousand kilometers, and these are called planetary embryos. Then in the final stage, around here, the gas has been cleared out from the disk, leaving behind just a bunch of planetary embryos. When the gas was still around, it tended to keep the orbits of the planetary embryos stable, fairly circular. But with the gas gone, the orbits of the embryos became more eccentric, allowing their orbits to cross each other, which allowed them the possibility to collide with each other, and then they could merge and turn into planets. So that brings us to here. So this is an extremely simplified version, and this is the gist of it. And many of these ideas are still valid. But this theory got a few things wrong. So if you look at this final picture here, one thing it got very wrong is that it assumed that the planets form in fixed orbits. They don't form in an orderly fashion. They form in fixed orbits where, and basically where we see them now is where they form. They didn't move around. They just stayed on fixed orbits. And the second thing that the theory got wrong is that it assumed that planet formation stopped at the last planet, whatever that planet happened to be, whether you call Neptune or Pluto the last planet. So it just assumed that planetary formation stopped there. And we'll see later on that these assumptions are quite wrong. But not everybody thought the solar system stopped at Neptune or Pluto. In 1949, an Irish astronomer named Kenneth Edgeworth speculated that it was unlikely that the solar nebula had a sharp edge at Neptune or Pluto. And if it didn't have an abrupt edge at these distances, there might be still be a swarm of small bodies beyond the planets. And this idea was brought up again by Gerard Kuiper in 1951. He pointed out that these objects beyond Neptune would not be planet-sized because the time scale for collisions between these bodies would be too long to form planet-sized bodies, so they would be smaller, perhaps on the order of comet size. So he said that the region beyond the planets would be filled with these leftover bodies that never grew into planets. For both Edgeworth and Kuiper, these speculations were not based on any calculation or any model. They were little more than inspired guesses. And maybe for that reason, both men's speculations went largely unnoticed, and the region beyond the planet was mostly ignored. But there was, But there was another solar system mystery that periodically brought up the issue of the outer solar system, and that problem was, where do comets come from? This is a picture of comet Ison, recently taken by an amateur astronomer. The comet is now inside the orbit of the Earth and is heading for perihelion at the end of this month at 0.01 AU, so very, very close to the Sun. So comets are small icy bodies orbiting the Sun, and we identify them by their large coma and their large tails. The coma is just a big cloud of dust and gas that surrounds the nucleus, and it develops when the comet approaches the Sun, gets heated enough that the ices in the nucleus evaporate. And as these newly released gas molecules escape from the nucleus, they eject dust particles, so filling the coma with gas and dust. And these dust particles reflect sunlight, and that's what allows us to see the coma. The presence of the coma tells us immediately two things. First of all, it tells us that the coma is full of ice, which means that it spends most of its lifetime somewhere far away from the Sun where the temperature is low enough that for the ices to remain frozen. Second, the comet is constantly losing mass. The dust particles and the gas molecules in the coma are not bound to the nucleus anymore. They have escaped from the nucleus and they're going to be lost into space. So with every orbit, each time a comet is heated by the Sun, it loses mass. A typical comet, like Comet Halley, say 5 kilometers in radius, has a mass about 10 to the 15 kilogram. When it's near the Sun and it's heated, it loses mass at the rate of about 10 tons per second. So at this rate, it would lose all of its mass. It would exhaust its complete body in about 1,000 years. Of course, no real comet loses mass at this high mass rate all the time. But it's only happened when the comet is near the Sun and is heated and it starts evaporating. But this simple approximation illustrates the fact that sublimation can cut short the lifetime of a comet to a lifetime that is much, much shorter than the age of the solar system. Furthermore, active comets are under the gravitational influence of the planets. And it's likely that a comet would end its life by, say, being ejected from the solar system, crashing into the Sun, or in the case of this comet Linear, it disintegrated when it approached the Sun, breaking up into many small little bits, or it could crash into a planet like this one. This is the case of Comet Shoemaker-Levy 9, who crashed into Jupiter. So all these dynamical end states happen on the order of about 500,000 years. So given that the average comets come to an end one way or the other in at most 500,000 years, so why do we still see so many comets? Something must be feeding the comets into the inner solar system where we see them. So the question is, where is this comet reservoir? This question is complicated by the fact that comet orbits are not all alike. And some have relatively large orbits, some have very small orbits. So astronomers roughly divided the comets into two groups. They're the long period comets, which take more than 200 years to go around the Sun, and the short period comets, which take less than 200 years. So this picture on the left shows the view of the orbits of a few large period comets. So if you can see the axes, right, the number go out to like 1,000 AU. So you can see that these orbits are very large. And the other thing noticeable about these comet orbits is that the orientation is completely random. So basically we say they're isotropically distributed. So if you can look at them from outside, they would look like a big spherical ball. At 100,000 so the origin of the long period comets is well established. In 1950, just based on these comet orbits, the Dutch astronomer Jan Oort deduced that they must come from a large spherical cloud with a diameter of about 100,000 AU. And this cloud is now called the Oort cloud, and it's the acknowledged reservoir of long period comets. At 100,000 AU, comets at the edge of the Oort cloud are almost halfway out to the nearest star. At that distance, the Sun's gravity is so weak that comets are susceptible to the gravitational tugs of passing stars and tied from the galaxy. So over the years, orbits in the Oort cloud have been randomized by these perturbers, giving them their random orientation. And that's why the known long period comet orbits look like that. So passing stars pass would deflect the comets on the outer edge. Some comets make it into the planetary system where we see them. Other comets just simply escape from the solar system into interstellar space. In fact, the size of the Oort cloud is set by the distance beyond which comets are ripped apart from the sun. So as shown on the right, these are the short period comets. And you can see that their orbits are much smaller than the long period orbits. They take less than 200 years to go around the sun. These are the comets that you see over and over again. And the two circles you see are the orbits of Jupiter and Saturn. So you can see get an idea how small the orbits are. And you can also see that the orbits are mostly confined to the ecliptic plane. So it's clear that these comets with their small, flat, fairly circular orbits are very different from these comets. The theory of the Oort cloud has been very successful at explaining the long period comets, where they come from, but it doesn't help the short period comets at all. At first it was thought that short period comets were simply derived from the long period comets by maybe some capture by the giant planets, but then detailed numerical work showed that this was not possible. And so the origin of the short period comets for a long time just remained unsolved. Every now and then, a few people, like these people, would conjecture that maybe a comet belt beyond Neptune might be the solution. But again, these were just mostly guesses. And so that was how things stood for a long time until the late 1980s. Around that time, Dave Jewett, who was my advisor at MIT at the time, he was just wondering why the outer solar system was so empty. The inner solar system, roughly speaking, the area from the orbit of Jupiter inward, was full of things. You have several terrestrial planets, you have the asteroid belt, and so on. But beyond Jupiter lay only a few giant planets and the oddball planet Pluto. And so as he saw it, there could be two reasonable explanations for the emptiness of the outer solar system. First, it could be really empty because of the gravitational influence of the giant planets. These things were so good at ejecting anything nearby that everything that was near them was just either kicked out of the solar system or scattered into a planet or something. Unfortunately, computers of the 1980s were too slow to confirm the validity, the long-term stability of orbits among the giant planets, so we couldn't verify this hypothesis, so it was a viable one. The other possibility is that the emptiness could just be an artifact of the vast distances in the outer solar system. We see solar system bodies because they reflect sunlight. So because of that, they become dim very quickly when you move them away from the sun. So if you take an object at 1 AU, like the distance between the Earth and the sun, and you move out to 10 AU, the brightness doesn't drop by a factor of 10 or 100, but it drops by a factor of 10,000. So since the brightness of solar system object drops so rapidly with increasing distance from the sun, maybe objects could exist out there, but they were just so faint that they escaped detection until now. So Dave told me his idea about the outer solar system, so we agreed to start looking for things beyond the giant planets. But first, we have to figure out how do we find these things. So at first, we thought that maybe the best way might be by occultation of background stars. In occultation, a solar system body passes in front of a star, and it temporarily blocks out the star's light, much like the way an extrasolar planet blocks out the light of the star that it goes in front of. So if you monitor the brightness of a star in occultation, you would see something like this. These are snapshots of stars that are occulted by asteroids. So if you monitor the brightness of a star, you see like this one, you see some constant brightness, and then it gets dim for a little while. This is when the asteroid goes in front of it, and after the asteroid has passed by, the star goes back to its regular brightness. And same here, same here, same here. And so we would be looking for dips in the brightness of these stars to indicate the presence of a distant object. But this bird, the whippoorwill of Arizona, put an end to our occultation strategy. We were observing in Arizona where these birds are very common nocturnal birds. I'll let you hear what it might sound like. Oh, there's no sound. Oh, bummer. Oh, there. Okay. Okay, so we heard that a lot. So we wanted to know about the effects of these birds on our occultation, and so we called the Audubon Society, and we had a very disappointing phone call. They revealed that occultation was not going to work. The real occultation were going to be too rare, too short, too similar to occultations by birds. So we had to come up with a new plan. So having no prediction of what we were looking for, we decided to use two methods for our search. First, we would use photographic plates. We would use them to photograph large swaths of the sky. Photographic plates are what astronomers used before large CCD cameras became available. They're simply glass plates covered by a light-sensitive coating. The good thing about them is that they're big. So a typical plate is like a foot by a foot. And a single photographic plate can cover a big area of the sky. The photographic plates we used had a field of view of 25 square degrees, which was about the size of 100 full moons. In addition to using plates, we would also use a CCD on a small telescope and a 1.3 meter telescope to find much fainter things. And CCDs are like, you know, the CMOS cameras you have in your cell phone. They're much smaller. They're about 1,000 times smaller than photographic plates. But it's also much more sensitive, about 100 times more sensitive. So by using both photographic plates and CCDs, we thought we would cover everything. We would target both ends of the size distribution. The photographic plates would be good at finding the bright but rare object, while CCDs would be good at finding the faint, hopefully abundant things. So, and we would recognize distant objects by how fast they move, because distant objects would move more slowly than nearby objects. So based on this speed limitation, we called our project the Slow Moving Object Project. Every sky survey is now done with CCDs, because astronomers now have access to very, very large CCD cameras like this one. This is a CCD camera that belongs to the Pan-STARRS telescope. It has 1.4 billion pixels. So this is the world's largest CCD camera. In comparison, this little dot is the size of the CCD camera that we originally used. In fact, it's smaller than this dot. I couldn't make a dot small enough. So anyway, so the idea of surveying the sky, which is such a small camera, with no guaranteed telescope time, was quite new. Whether with photographic plates or CCDs, the technique to find moving objects is the same. You look at a sequence of images very rapidly so that any object that moves from frame to frame would stand out quite clearly. And this process is called blinking, and it's a traditional way to identify solar system objects. So these are the photographic plates that discovered Pluto, and you can see the arrows. So you can see the way to find moving object with photographic plate is you look at every single dot, and you hope that one of them moved a tiny little bit. And this was not fun. So with CCDs, it was better because we have electronic images, so we could use a computer to help us do the blinking. And so these, I'm going to show you a sequence of CCD images, and they were discovery images of real Kuiper Belt objects. This is not working for some reason. Okay. Okay, I don't know why this is not working, because it was working before. So this should show that this object moves in a sequence of CCD images. So I hope this problem doesn't occur to the other movies. Okay. Okay, we started our survey at Kitt Peak in Arizona, but in 1988 we moved on to Mauna Kea, Hawaii, where we have access to a much better site. This is Mauna Kea, and our telescope now was a University of Hawaii 2.2 meter telescope, this one. And now we have a bigger telescope, we had a better site, so we had high hopes that our survey would yield something. The title of this slide is How to Pursue Unfunded and Unpopular Projects, and that's what our search was. Telescope time committees and funding agencies did not look favorably upon searches for objects that were not predicted by anything or anybody. Friends and colleagues and the telescope operator kept asking us when we were going to quit, because we were just wasting everybody's time. So we procured telescope time any way we could, mostly by stealing from ourselves, so it's okay. We would write telescope proposals saying that we would do work on some project, and then we would steal some of the time from that project for our search. And so this went on for many years. So for postdocs and grad students who don't know how to fund unpopular projects, this is a way to do it. Okay. So After 5 years of fruitless searches in the late summer of 1992, there was a new camera on the telescope. This was a CCD with 2,000 by 2,000 pixels, 22 more times pixels than our first device. And the first time we observed with this CCD camera, we found our first Kuiper Belt object. This figure shows the 4 discovery images, and the times of observation are indicated here. The strategy was that we would take 4 images of the same area of the sky, spaced out over a few hours. We needed at least 3 or 4 images to confirm any detection, because there were many possibilities or artifacts like cosmic rays that would mimic the slow-moving objects. So we had taken just the first 2 images of the sequence, and Dave was blinking them on the computer while the 3rd exposure was on the way, and he noticed a candidate right away. The object has all the right characteristics. It was moving westward. It was moving very slowly, about 3 arcseconds per hour. And it was faint enough that it was unlikely anybody had seen it before, but it was faint, so it's unlikely anyone had seen it, but it was so bright enough that we knew it was not noise in the image. And then the 3rd image came out, and it was still there. And then the 4th image came out, and it was still there. It was still moving in the same direction, the same speed, had the same brightness. So that's when we knew that the object was real. So by the end of the night, we knew that we had found a solar system object beyond Neptune, more distant than anything seen before. Based on the object speed, we could calculate how far away it was, and it was at 41 AU, far beyond Neptune. And from its brightness, we could estimate how big it was. It was about 250 kilometers. And the new object came to be called 1992 QB1, based on the order of its discovery in 1992. And the population to which QB1 belongs is now called the Kuiper Belt. By now, more than 1,500 Kuiper Belt objects had been identified as a result of many searches by many people all over the world. The known objects are typically about 100 kilometers in diameter. The total number of these objects is about 10 to the 5, 100,000. And if you go down to the 1 kilometer size, there are 10 to 100 million of these things. Several Pluto-sized bodies have been found. Altogether, the total mass currently contained in the Kuiper Belt is about 0.1 Earth mass. This is much larger than the mass contained in the asteroid belt, but it's still much too small to form Pluto-sized bodies on a reasonable time scale. So we believe that the original Kuiper Belt must have been much larger to produce such large bodies. The current explanation is that the modern day Kuiper Belt is just a remnant, a much more massive Kuiper Belt, 100 to 1,000 times more massive, amounting to about 10 to 100 Earth masses. Just to give you an idea, 100 Earth masses is about the size of Saturn. The Kuiper Belt itself is a thick ring, it's like a donut-shaped ring of icy bodies, extending roughly from Neptune's orbit all the way out to beyond 1,000 AU. The thickness of the belt is about 25 degrees to 30 degrees. And this is evidence that the Kuiper Belt object have been stirred up. The orbits of the Kuiper Belt object have been stirred up because the inclination are substantial. The current relative velocity in the belt is about 2 kilometers per second. With this kind of relative velocity, collisions in the belt are primarily erosive. That means that when 2 things collide, they shatter. They don't stick together and grow bigger. So at that point, now we know we have found 2 sources of comets to explain the 2 groups of comets. So you have the Oort cloud extending all the way out to about 100,000 AU at the edge of the solar system. And if you go really, really close in, then you get the Kuiper Belt that looks something like this. So this plot shows what Kuiper Belt orbits look like. If you can look from the North Pole, looking down the ecliptic, and what you notice immediately is that the orbits are not all alike. Some are big, some are small. Okay. The diversity in Kuiper Belt orbits can be really seen in these plots, and these plots are probably the most important and also the most surprising results that came out from the Kuiper Belt work so far. On the left, we have semi-major axis here plotted against eccentricity. So the semi-major axis tells you how big the orbit is. The eccentricity tells you how elliptical an orbit is. So 0 eccentricity is down here. This is indicates a circular orbit. And over here we have semi-major axis plotted versus inclination. So these plots show very clearly that the Kuiper Belt has been extensively sculpted, primarily by Neptune. The orbits are highly organized. They're not randomly distributed in semi-major axes. They're well-defined gaps and concentrations. And based on these very different orbit types, we have managed to classify Kuiper Belt orbits into 4 different groups, and they're color-coded. Okay? So first, here are the objects in red. These are the classical objects. They're clustered roughly between 40 and 50 AU. Their eccentricity goes up to about 0.2, while their inclinations over here goes up all the way up to about 40 degrees. And the inclination distribution seems to be bimodal. That means there seem to be 2 different groups. There seems to be a group clustered to be like with inclination less than about 15 degrees, and there's another group with inclination larger than about 20 degrees. So the fact that these 2 inclination distributions seem to suggest a complicated origin for these guys. So they're not, they might come from 2 different sources. Another interesting thing about the classical object is that they seem to have a sharp edge around here, about 47 to 50 AU. And this is not due to any observational bias. That means that our telescope surveys should have been able to discover things beyond here, but haven't. And the cause of this edge is not known. It could be this is where the primordial Kuiper Belt ended, maybe, or maybe the Kuiper Belt was truncated by a star that passed nearby. We don't know that, but for sure either. Or maybe there are things beyond this edge, but say for some reason they're much smaller than the other ones. So they're beyond our detection capability. So we don't know which explanation holds. And then there are the big highly elliptical orbits. Those are the green and the black. So the green object, these are the scattered object, and the black object called the detached object. Both groups have highly elliptical, very large orbits, but they differ. The green ones cluster in this arc. These arcs indicate the perihelion distance of 30 and 40 AU. So basically, everything in this swath makes close approaches to Neptune. So we know that it's continued interaction with Neptune that throw these objects, that scatter these objects into the highly elliptical and inclined orbits. The largest aphelion, the largest distance reached by one of these Kuiper Belt objects is about 1100 AU, so it's quite far. So this group is believed to be the source of the short period comets. Below this line, we have the black object. These are the detached objects. And they're different because they do not make close approaches to Neptune, but they still have very large, highly elliptical orbits. And so we don't know what gave them these extreme orbits. Again, lots of theories have been proposed for their origin, including perturbation from a massive, undetected planet, or maybe it came from closely passing stars, or maybe just more mundanely, resonance dynamics. We don't know, and I'll talk a bit more about resonance dynamics pretty soon. The blue objects lined up vertically here are the resonance objects, and they're located in the mean motion resonances marked by these vertical dashed lines. There are many mean motion resonances. I just indicated a few here, and these are the most populous ones. The name of the resonance are located at the top. So let's take the 3-2 resonance, for example, here, okay? Objects located in the mean motion resonance have a special relationship with Neptune. So objects in the 3-2 resonance make 2 orbits around the Sun for every 3 orbits completed by Neptune. And the most famous inhabitant of the 3-2 resonance is Pluto, indicated by this red P. And there's similarly things in the 2-1 resonance would make 1 orbit around the Sun for every 2 orbits completed by Neptune. So why does this matter? Well, what happens is that when you have a small periodic force occurring at a resonant frequency, the force acts coherently in phase over and over again until it effectively becomes a big force, okay, and then with a big effect. Now try it. Oops, okay, so this works, okay. When the orbital periods of 2 bodies form a ratio of small integers, like 3 to 2, 2 to 1s. You have a recurring geometry, and I'm going to show that here. So this is going to show you the recurrent geometry that you get with 2 planets, when you have 2 planets moving in a 2 to 1 resonance. And this is actually the geometry of an exosolar planetary system, GJ 876, which has 2 massive planets with orbital periods of 1 month and 2 months. Okay? So these dots, so the red and blue dots are the planets, the black dot is a star. And as a consequence of the 2 to 1 resonance is that when the 2 planets come to perihelion, the star and the planets lined up in a perfect straight line, and this is called a conjunction. And you're going to see how this configuration is maintained as the planets go around. Okay. And this now. Okay, I don't know why this is not working even though the movie is running. Could somebody in the AV room come help with this? Yeah, okay. This is not good. What this is supposed to show is that, so for every orbit that the blue planet makes, the red one would make 2 orbits, and they just go around and around. And as the planets go around, this conjunction geometry would repeat, even though the whole system precesses around. But this geometry repeats over and over and over again. And that is how mean motion resonances amplify their effect. So that's how they pump up the inhabitants' eccentricity and inclination, because the gravitational effects get amplified over and over again by a recurring geometry. Okay, I want to show again, emphasize again, how the fact that Pluto is in the 3 to 2 resonance. If I did not mark it with a red P, you wouldn't be able to pick it out. And this is, I think, more than any argument, this plot proves that Pluto is much better understood as a Kuiper Belt object rather than a Pluto. You probably know that Pluto's orbit crosses the orbit of Neptune, but thanks to the resonance, the 2 objects never collide. And so Pluto is always protected from colliding with Neptune. And this protection applies to all the other objects in the 3 to 2 resonance. And they're called Plutino to emphasize their similarity with Pluto. Resonant objects are especially important because they provide strong evidence for something called planetary migration in our solar system. Planetary migration is not a new idea. It was first shown by Fernandez and Ip in 1984 that if the gas was not around, if the nebular gas had been dissipated, the orbit of the giant planet had to shrink or expand as a result of scattering all the nearby primordial planetesimals because of conservation of angular momentum. So they proposed this back in 1984, but the idea did not catch on until Renu Malhotra used the resonance Kuiper Belt objects to show the magnitude of planetary migration in our own solar system. So let's consider the late stages of planetary formation. This happened about after 10 million years or so, when the giant planets had reached mostly their current masses, but there was still a residual swarm of primordial planetesimals everywhere. So something like what this picture shows here. So interplanetary space would fill with a huge amount of debris, basically things that had not had a chance to coalesce into a planet. And naturally, the giant planets, being so massive, were very good at tossing this debris around. So if you take Neptune for an example, when it scatters something, there's an exchange of angular momentum between it and the planetesimal it scatters. Some planetesimals are scattered outward, some are scattered inward. In an inward scattering event, the object is transferred to a smaller orbit. So this means that some of its orbital energy has been transferred over to Neptune. So Neptune gained some orbital energy, and its orbit expanded very, very slightly. This inward scattered object would usually tend to make its way all the way in toward the sun. And as it moves inward, it gets scattered by the other planets in turn. So first, it gets scattered by Uranus, and it gets scattered by Saturn, and then finally it makes its way to Jupiter. When it reaches Jupiter, due to Jupiter's enormous mass, this planet tends to eject the planetesimals completely out of the solar system. And in ejecting the orbit, Jupiter loses energy, and so its orbit shrank a tiny little bit. And the opposite scenario happens when an object is scattered outward. But in the end, it's the inward scattering events that are more common. So we'll just ignore the outward scattering events for now. So in the end, the inward scattering events dominated. So the net effect is that the orbits of Neptune, Uranus, and Saturn expanded because they gained energy, while Jupiter's orbit shrank because it lost energy. Neptune moved outward on the 10 AU, which is quite substantial, considering that right now it's at 30 AU, so maybe originally it was at 20 AU roughly, so this is a big move. Uranus and Saturn also move outward, but because they're more massive, they moved out, they expanded a smaller amount. Jupiter's orbit shrank, but due to its enormous mass, its orbit only shrank by a little amount, like a tenth of an AU or so. As Neptune moved outward, its mean motion resonances get pushed ahead of it. So, these resonances just plunge into the primordial Kuiper Belt. And as these resonances swept through the Kuiper Belt, they captured Kuiper Belt objects, much like a snowplow sweeping up snowballs. The number of objects captured inside the resonances is indicative of how far Neptune moved. That's how we were able to calculate how far Neptune moved, just because we could measure the population of the mean motion resonances. And so this shows you what the configuration of the giant planets look like before migration. So the giant planets on nice tight circular orbits. And after migration, the planets got spread out a bit more, and then Pluto got captured into this orbit. And it developed this orbit as it was shepherded outward by the mean motion resonance. Okay. Is this going to work? Darn. That doesn't work either. I'm sorry about that, but you can find it on YouTube. Okay. Okay, so I have to describe what you can't see. Planetary migration is now very much in vogue, and it has been proposed to explain almost everything in the solar system, from bombardment on the moon to the distribution in the asteroid belt, to the size of the terrestrial planets. So it's very much the in thing to talk about. So there is little doubt that planetary migration occurred in our solar system, but the question is how much, when? And here's one model that has received a lot of attention. It's called the Nice model. It's not the nice model, it's the Nice model. It's named after the French city, and it is quite a popular model. It proposes that the giant planets were originally surrounded by a swarm of a big disk of planetesimals, about 35 Earth mass, just beyond the orbit of Neptune. But I have to point out something. This blue circle, that's Neptune. So in this scenario, Neptune was not the outermost giant planet. It was just inward, so it was here, and this is Uranus. So according to the scenario, okay, so there was this huge planetesimal disk. So of course the giant planets started tossing them around. They started scattering these objects. And as the giant planets scattered these objects, the orbit started moving, a little bit. And eventually, the Jupiter and Saturn crossed the 2-to-1 resonance. And when these two massive planets cross the 2-to-1 resonance, of course, their orbits completely changed. The eccentricities of the orbits got pumped up highly, so their orbit become highly elliptical, allowing them to move in and out quite a lot. And that had a drastic effect on everything else in the solar system. So Jupiter and Saturn started scattering the ice giant, Neptune and Uranus. So these two planets developed highly elliptical orbits, plowed into the Kuiper Belt, swapped places in the solar system, and then ends up with this. So now since they swapped places, and so Neptune now ended on the outside and Uranus on the inside. So that's the Nice model. Okay. So maybe this scenario happened, maybe it didn't. But the point is now the possibility is open, right? Because before we didn't think that this could ever happen, but now after we discover the Kuiper Belt and we understand that planetary migration plays a big role in solar system evolution, this is a possibility. Okay, the next question I'll address is the Kuiper Belt a special feature of our solar system, or does it also exist in other planetary systems? It appears that the Kuiper Belt is a universal phenomenon and is common to planetary systems. In the early 1980s, even before the Kuiper Belt was discovered, dust disks were observed around some main sequence stars. This is like older than 10 million years or so. And the most famous of which is Vega. So these dust disks are often called a Vega-like disk. And so this picture shows the three most famous dust disks, Vega, Fomalhaut, and Beta Pic. So dust is common around young stars. That's not a big deal. But the reason these dust disks attract a lot of attention is because they're quite different from the dust around young stars. This dust is cold, about 50 Kelvin, and it contains big grains, much bigger than the grains that you commonly encounter in interstellar medium and around young stars. The dust is in flat disk rather than a spherical shell. And finally, the dust has a short dynamical lifetime, and so it had to be replenished somehow, most likely by collisions between planetesimals around the star. In other words, these dust disks are evidence of planetesimals around stars. They're debris disks. But at that time, the nature of these planetesimals were not really understood because we didn't know of any massive population of cold, icy cold planetesimals in our own solar system. So people didn't know what these planetesimals were until the Kuiper Belt was discovered. And now we've realized that these dust disks are basically extrasolar analogs of the Kuiper Belt. This plot compares the dust disk around Vega with our own solar system. This has been expanded by a factor of 4. So you see that the Vega system is very much like our own. So you have 2 debris disks separated by a gap. Okay, these 2 debris disks the outer one is at about 100 AU, like 100 to 120 AU, and this has been identified as Vega's very own Kuiper Belt, and it contains cold dust. The smaller belt on the inside, very close to the star, it contains warm dust, and the most plausible explanation for this warm dust is that it's dust produced by an asteroid belt. And the simplest explanation for the gap between the 2 disks is the presence of planets, multiple planets, as yet undetected. And these planets would play the same role as the giant planets in our own solar system. They remove dust grains, and they prevent the formation of other dust belt between the 2 massive ones. And I should mention that Kuiper Belt dust has been detected in our own solar system by the 2 Voyager spacecraft. Voyager 1 and Voyager 2, on their way out of the solar system, detected impacts by dust particles. And at the time, the people who saw this data had no idea where the dust came from. But now we know that this dust is just simply dust based from collisions of Kuiper Belt objects. And the dust in our own Kuiper Belt is much less massive than the dust that you see here. It's about 1,000 to 1,000 times less dust than in the Vega disk. The obvious question to ask at this point is, what else is out there, now that we know the giant planets have scattered away a huge amount of mass? So this drawing shows one version of the known content of the outer solar system. So you have the planets, the asteroid belt. We know everything out here. Okay, so here's a Kuiper Belt, and we know that it's like a thick disk. And then something has to happen here, and then you get out to the Oort cloud, and we know that's spherical. So we know up to here, and then we know this region here. Okay. At 100,000 AU, there's little chance of observing anything directly in the Oort cloud. If you take comet Halley and you put it out at the Oort cloud, it would have, at 100,000 AU, it would have magnitude 64. So let's bring it a bit closer, say 1,000 AU, it would have magnitude 43, quite a bit brighter, but still far beyond the detection capability of any telescope that might be built by current technology. Even stellar occultation would not work because the angular diameter of the comets at such large distances is very small compared to the angular diameters of stars. Conceivably, Earth-sized or even larger bodies might have been scattered out into the distant regions of the solar system. And this picture shows you another artist's conception of what the outer solar system might look like, but this time on a log scale. Okay? So this shows you the scale of the vast regions of the solar system in which large objects might still exist and yet remain undetected. So the outer edge of the Oort cloud, here, 100,000 AU, here's the nearest stars. Here's Voyager 1. Voyager 1 is now at 125 AU. It has officially entered interstellar space last year when it crossed the heliopause. We can place limits on how much dark mass might still lurk in the solar system based on optical surveys and based on gravitational perturbations, okay? So they're the two equations that you would use. So you can see that based on gravitational perturbations, the mass limit scales as the distance r raised to the third power. But it's an optical survey, it goes r to the sixth. But so you would think, this might be a better method, but I'll show you that's not the case. So this table shows you, first I'll talk about this column, this R24. It shows you the distance at which these objects would have magnitude 24. So for example, Earth would have magnitude 24 if you move it out to 620 AU, which is about only 10, factor of 10 beyond the largest, the most distant known Kuiper Belt object. And at 24 AU, Earth would not, it would still remain undetected because there's no existing all-sky survey that would have picked it up, okay, at magnitude 24. So this column is our gravitational, and this is the distance inside which the gravitational perturbations by these objects would be felt based on the orbit, perturbations on the orbits of the giant planets or comets. And this shows that. So that's calculated from this equation here. And you can see that our gravitational is less than R24. So in contrast to what many people assume, that unseen massive planets might be better detected by their gravitational perturbations, that's not the case. Optical surveys at this point remain the more sensitive method if you can reach magnitude 24 and if you had an all-sky survey. This is exactly what the Large Synoptic Survey Telescope would do, if it ever gets funded and it starts working. So if it gets built, if it works, then I think it would be able to pick up Earth as far out as 620 AU. So what this table says is that our current limits on the solar system contents are very poor, and the possibilities are basically endless. These limits are very small compared to the scale of the outer solar system. So at first look, you look at this table and you say, oh, that's kind of depressing because we don't even know our own backyard. Forget talking about the origin of the universe. But on the other hand, this table can also be read as a kind of good news because the Kuiper Belt has opened up a huge volume of space, basically unexplored, where all kinds of things might lurk and just await discovery. So, in other words, the solar system, in contrast of what George might think, is an exciting place. Sorry, George. With many discoveries waiting to be made. And I'll just end my talk on that optimistic note.
Oh, thanks, Jane. So we've got time for a couple of questions. Anybody has questions? Yeah, let's take one at the front.
You've talked about the possibility of this scattering. Sorry, thank you. The Nice model suggests that Uranus and Neptune may have swapped places about a billion years after the formation of the solar system, so about 20% into its life. How does that compare with the migration of the outer planets that you mentioned? And also, could that swapping have been a gravitational event that might have been a partial mechanism for the scattering of the outer bodies in the Kuiper Belt?
That's exactly it. They coincide. If you go to YouTube and you look at the model, you can see how the whole thing happened. So it's just all part of the planetary migration process. Jupiter and Saturn crossed the 2-to-1 resonance. Everything, all hell broke loose. Uranus and Neptune got ejected into and plunged into the Kuiper Belt, scattered everything away, leaving behind what we now see, and it used to be a massive planetesimal disk. And so there was a lot of this scattering everywhere. And in fact, this model was also used to explain the late heavy bombardment epoch on the moon. Right? People have seen that there was an epoch of heavy bombardment on the moon. We can see that from the craters. And the Nice people have proposed that this could explain everything. It could explain Uranus, Neptune, the terrestrial planets, the asteroid belt, bombardment on the moon, everything.
Any other questions?
Martin.
You mentioned that you could detect planets way out beyond 100 AU. Is there any scenario where something as big as a planet could actually form out there?
No, they would not form out there. They got scattered out. Okay.
Can you take one more question at the back?
Hello. It's just a general question, really. It's knowing whether you agree with Albert Einstein when he said science is blind without religion, and religion is lame without science.
What does science have to do with religion?
Sorry?
I have no idea.
Well, Albert Einstein, he did say that science without religion is blind.
I think he's referring to your belief that you were going to see something. You had a long-standing belief you were going to see something. That's a bit like religion.
No, we didn't believe we would see something. We were just wondering why the outer solar system was empty. We were prepared to find whatever was to be found. If it was empty, okay, it was empty. That's good to know. And if it wasn't empty, that's good to know too. We were just looking. We didn't believe anything. we're not religious people.
Let's take one last question down here.
Are we within the interaction distance of any other star's Kuiper Belt?
Insofar as it's unlikely that in the present environment any star would come so close to the sun that it could have, could truncate the Kuiper Belt or scatter something out in this current environment. But there is some evidence that the sun was not born in this environment. It was born maybe in a more populated environment, like a cluster. In that scenario, it was highly likely that there were nearby passing stars that could have had big effects on the outer solar system, like truncating the Kuiper Belt, scattering things out into the outer regions.
Okay, thanks. Well, most of us, as professional scientists, if we do anything that merits a footnote in a technical monograph, we will have had distinguished careers, perhaps even elected to learned societies like this one. But Jane's research has actually made it to the schoolroom. Now we have a generation of kids that know that Pluto has been demoted to a dwarf planet, along with other dwarf planets like Haumea, Ceres, and Makemake. So her research has really revolutionized our understanding of the solar system, and it's been wonderful hearing from you. So thank you very much, Jane.